What we call detection is you want to identify and locate objects in your image. So to take an example, that we talk to everyone, let's say you have some drone imagery of a city and you want to map and count the buildings. So what you expect as an output is basically a polygon around each building in the city. And then from the polygons, you can then process them in a GIS software, make them into a web map, do whatever operation we want.
Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. My guest on the show today is Julien Rabatte, and apart from being a victim of my terrible pronunciation, Julien is a software engineer and a machine learning expert at a company called Pictera. And today we're going to be talking about a tool that they've created, some software they've created, which allows you to build your own object detection algorithms and run them against a variety of different data types. Like me, Julien has a slight accent, so please listen carefully. I think this is really exciting stuff, what we're going to be talking about, what you're going to hear in this conversation. I feel like this is object detection, this is machine learning for the rest of us. So after listening to this podcast episode, if you decide this is something that you want to try out for yourself, want to be involved with, head along to Pictera/Mapscaping, and they've made a rather generous offer, I think. So 500 free credits, so you can try it out for yourself. They're really looking for user feedback on a couple of the add-ins they've developed for ArcGIS and QGIS, and anyone out there listening could help them out with that. I know that it would be greatly appreciated. So I'll put a link to that website in the show notes, of course. But if you just want to go and search for yourself, it's pictera.ch/mapscaping. But again, there'll be a link in the show notes. You can click on that too if you're interested. Okay, let's get on with the episode. Hi, Julien. Welcome to the podcast. Thanks for taking the time to talk with me today. It's much appreciated. You work for a company called Pictera, and you guys are doing something really interesting. It's almost like a build your own AI for object detection using aerial and satellite imagery. And I think this is an incredibly interesting concept, and it's a really interesting implementation. But before we dive into all that, perhaps you could just take the time to give the listeners an understanding of your background in geospatial.
Sure. But first, thanks for having me at the podcast. Really happy to join. So I guess I started in geospatial 10 plus years ago during my bachelor thesis, actually, which was about deforestation detection from satellite imagery. At the time, it was low resolution satellite imagery. That's when I got exposed to geospatial, but also to machine learning in geospatial, because basically we were looking at image and trying to classify deforestation. After that, I worked a bit with deep learning applied to drone imagery, and more specifically trying to classify crop types in drone images of agriculture and farmlands, basically. And then I basically joined Pictera 3 years ago. And so I've been leading both the machine learning and the software engineering side of it. And so I've been exposed to a wide range of geospatial data. We get TIFF data, we get web map services data, we get RGB data, we get infrared, digital surface model, and a super wide range of data. And then we are trying to make machine learning work on all of this kind of data. And so that's basically what I've been doing for the last 3 years. So I learned a lot about machine learning and the specificities of machine learning applied to geospatial. And so, yeah, that's where I'm right now.
So it sounds like you've got a really good background in this, and like the idea of applying machine learning to aerial imagery, to satellite imagery, to imagery in general is, it's an exciting time in terms of that right now. And I think what I found particularly exciting about your approach to it, or Pictera's approach to it, is this low code, no code, so you're giving access to people like me that don't necessarily know a great deal about machine learning to make your own, to do this object detection. And we're going to unpack that in just a second. But I think we should start off with what kind of data that we can use. So if I go to your website, it's kind of laid out for me. It says, data detection results kind of thing. So let's start with that. Let's talk a little bit about the data. What kind of data can we use to create our own object detectors?
To start off, there are two big categories. One category is that you have an image file on your hard drive, on your computer, and you can upload it to Pictera. And typically, you would have a GeoTIFF, like the output of photogrammetry software, like Pix4D or Drone Deploy, or something that you got from a satellite image. provider. So that's one category, is you have a GeoTIFF and you can upload it to the platform and then build your machine learning model on it. The other big category is more streaming data. And so you can connect many kind of servers to Pictera. So for example, you can connect a web map service, a WMS server to Pictera. We can also process XYZ data. It's a popular format for web map. And so you can, that's basically the two big categories. Either it's a file or it's a remote server that we can connect to. And then depending on where the data comes from, we support a wide range of let's say, sensor types if you want. So it can go from drone data. So we have people uploading 1 centimeter or even like sub-centimeter drone data, so super high resolution data. We also have people working more on aerial data, the typical stuff. I mean, in a lot of countries, they make some aerial mapping campaign every year or something, and you can process it on Pictera. And then we also connect and have people working with satellite data. And usually the resolution is a bit lower for satellite data. So like 25 centimeters for the 30 centimeters for the commercial satellite, the highest resolution you can get. And then you go down to like 10 meters for Sentinel-2, which is freely available. So yeah, that's a bit the range of data that we support on Pictera, and we try to really support any kind of geospatial imagery data, let's say.
So a couple of things that stuck out for me there. The first one being that you support flat files and these streaming services. And it seemed to me that a lot of this support is probably based around the RGB bands, the visible spectrum. Is that the correct way of understanding this?
So it's the correct way in the sense that this is what you will mostly visualize. But basically, the platform is built around visualizing and processing 3 bands. So the natural way is that these 3 bands, they are RGB, because that's what you're used to look at. But I mean, technically, you can completely do a false color image. So it means instead of having RGB, for example, you have RG and then a near infrared band instead of the blue band. And so this is a false color image that you can upload to the platform and train a detector on. And actually, it gets more interesting because it's not limited to visual data. For example, you can make a composite image that has some visible bands, and then the last band can be a digital surface model, for example. So that's also a way to process more elevation data through Pictera.
Yeah, I think that's a really interesting idea too. So we got 3 bands we can work with, and it sounds like it doesn't really matter what's in those 3 bands as long as it's in a pixel format, of course. So elevation data, perhaps temperature data, maybe even a classified image that you're putting together with some other data and just pushing it together into a 3-layered image and sending it off to Pictera. Yeah, so that really, really interesting stuff. I love the idea of using these streaming services as well, and especially like a web map service. And I want to talk about that in just a second. We have a bit of an understanding of the kinds of data we can use to do this object detection. Perhaps you could talk a little bit about the detection itself. So this is a bit of a black box for some of us. What is detection for you?
That's a really good question. So basically what we call detection is you want to identify and locate objects in your image. So to take an example, I mean, that we talk to everyone, let's say you have some drone imagery of a city and you want to map and count the buildings. So what you expect as an output is basically a polygon around each building in the city. And then from the polygons, you can then process them in a GIS software, make them into a web map, do whatever operation we want. So detection is really like from the image, automatically extracting geospatial polygon information, I would say. And so there is a whole process of training a detector on the platform where you kind of have to teach the machine learning model what you're looking for by giving it example. I mean, it's really similar to training a human or to teaching a small kid about the world and about what you're interested in. So you give example, you see how the machine learning model does, and then if it doesn't do very good, you can give more examples. So there is also a bit this iterative approach to it where you try, you start, and then you kind of iterate until you get good enough results.
Okay, so from what you just said there, we're teaching the machine what an object is. So we're taking this continuous data imagery of the world, probably, and we're trying to find discrete objects in it. So some people might refer to this as segmentation or labeling, and it seems to me anyway that this is a bit of perhaps a supervised classification method. So if I've understood this correctly, we have imagery of some type, and we're going through and training the machine ourselves. So when we train the machine, we're labeling objects that we can see in the imagery. Are we drawing bounding boxes around these objects, or do we have to draw very tight, detailed polygons around them? Is that what the process looks like?
Yeah, so what you do on the platform is you draw a somewhat detailed polygon. I mean, you don't have to go crazy and be pixel perfect with the polygon, but basically you draw a polygon, and then the model, it will output polygon. And I think that's maybe a big difference with what people have in mind when they talk about segmentation and per pixel classification, which is something you have in a lot of GIS software. What we use under the hood to do the machine learning, we use some deep learning model basically. And the model, it will not only look at the pixel, so it's not a per pixel classification, it will also look at the context, and the model will output a polygon. So that's really the big difference, is that you don't get per pixel information, but you really get a single object as a polygon as the output, and the model is also considering the context. And this usually gives it a much higher accuracy than a per pixel approach, where you very often have a lot of noise, let's say, in the classification output.
That's really interesting that you're not just looking at the pixel signature itself, but also the adjacent signatures, I guess, or the neighborhood that pixel is in. I think you referred to it as being the context of that object. I think that's really interesting.
Yeah, exactly. And that's actually the power of deep learning, if you want, in that you kind of give the machine learning model a lot of freedom to pick whatever seems to make more sense for the object you're trying to detect. So if you try to analyze what the model is learning and what it's looking at, so first I have to say this is still very much an academic research topic, so we don't have all the answer to really understand exactly what's going on. But you can look a bit at what it's looking at, and in the first stages, you can divide it in stages. And in the first stages, it's mostly looking at stuff like edges and sharp difference in contrast in some region. So imagine you have a building, there will be an edge between the roof and then the ground, let's say, the grass or whatever is around it. And so in the first stage, the model is a bit looking at this like strong difference in contrast and edges. And then as you go deep in the model, and that's where the deep learning stuff comes from, as you go deep in the model, it's learning to basically combine this high level feature into more like shapes. So at some point, it's probably gonna look for stuff that is a bit square, let's say, because buildings are usually square and they usually have kind of a fixed, not fixed size, but let's say they have a minimum size and so on. And so as you go deeper in the model, it's basically building kind of a hierarchical understanding of the object you want to detect. And that's how at the end you can get this really good quality detections.
Okay, so we have our data and we're labeling the images. I think one of the things I found really exciting about your platform is that it could happen on your platform through the website, and you also have these plugins to ArcGIS and QGIS. So in a piece of software that I'm familiar with, I can go in and I can label these objects, draw polygons around these objects based on either some data that I have, so a flat file, or on a streaming service. So let's think about a web map service. So we're streaming data in, we're labeling objects, then what happens?
So I mean, if you're doing the labeling in QGIS or ArcGIS, there are basically two ways to get this data in the platform. So one is through the plugins, which should basically facilitate this. They are still a bit in development and in beta, so we are also looking for feedback on the plugins if any listener is interested. But so either you go through the plugin, or you can also directly upload some GeoJSON vector data in the platform as training data, basically. So it's quite open how you get your training data in, and it means you don't have to redraw everything on the platform. So, for example, if you're a company and you already have, let's say, building outline for the city, you can actually reuse this existing data as a way to train a detector, and you don't have to spend 10 hours redrawing the whole city on Pictera.
If I take a very practical example now, let's say I have a web map service for Paris. Very detailed data, it's aerial imagery, RGB imagery. And I go to something like OpenStreetMap, download all the building polygons for Paris. And can I use that then to select the training data I'm going to use for the machine learning for the detector based on this web map service I have of Paris?
Technically, yes. So technically, you will need to do is you will need to turn the OpenStreetMap data into some GeoJSON, or you could write a script to upload it to Pictera. We also have an API, so you could write a script and ingest it in Pictera. And then you will have to connect the WMS to Pictera. That's also fairly easy. And then you're able to train a detector from the WMS from Paris and the OpenStreetMap data that you ingested in Pictera. If you're talking about OpenStreetMap, like specifically, they have some legal constraint around what you can do with their data. So you should check this before actually doing this, I would say.
Yeah, I was just trying to use that as an example, like as a known data source where geospatial professionals, we know and we understand OpenStreetMap and we see it as this huge resource. And I'm just thinking about how could I quickly get, if we're talking about building classification, for example, how could I quickly get a whole bunch of building footprints and sort of speed up the process instead of manually going in and saying, this is a building on my web map service of Paris. I'm just kind of thinking ahead and say, well, I wonder if we can speed up the process here.
On buildings specifically, there is a lot of cities around the world, or even countries actually. For example, in New Zealand, they have basically open WMS that you can access with the imagery, but you can also access the cadastre data for the whole country, if I'm not mistaken, or at least a very big part of the big cities. So this cadastre and aerial data that a lot of cities or countries have is something that you can then ingest into Pictera. So that's a really good way to get started on if you want to train a detector on buildings or on something that's in the cadastre, let's say.
Can you talk a little bit more about the training process? Because I think we understand now that we can go in and we can select these objects manually, or we can use a known data source to make that selection. But what does the training process look like? Because I'm imagining anyway that it's unlikely I'm going to get it right the very first time.
Yeah, usually you have to do a few iterations. So the way it goes is you log in on the platform and you can train the detector. And what you can do is you can do two things and that are very similar to what you do if you're a machine learning engineer trying to train a model. But there is a UI to help you do it in a very simple way. So one thing is defining the training data. It's what we just talked about. So like having some annotation, having some imagery. But you can also define what we call accuracy areas. And these are basically areas that you have to annotate as well. So you have to have labels for as well, but we'll evaluate the accuracy of the detector in this area as you train it. And so you get kind of a score at the end of the training to tell you how good the detector is. And so usually the way training works is you upload the first set of training data, or you draw it, whatever, and then you train the detector and you will check what's the accuracy in the accuracy areas. And from there, you can annotate more and basically iterate until you get good results. Let's say that's the basic workflow of training a detector.
Again, with the idea of speeding up the process here, can I add any other sort of geographical constraints? Can I say that I'm only interested in this area or don't look in this other area?
Yeah, you can do this currently at detection time. So we have something called detection areas, which is a way to constrain the detector to only look into basically polygon again that you give to the detector. So for example, let's say you want to detect solar panels on buildings. Typically what you would do is you would train a solar panel detector, but then you would use the building footprint as the detection area. And so the detector will only look for solar panels that are within a building footprint. And so what this allows to do two very interesting things. So the first thing you can do with this is when you train your detector, you don't have to bother making it good outside of buildings. So it doesn't matter if it misdetects some stuff that's on the road or whatever, because you will have detection areas when you run the detector. And the second thing that it allows you to do is you can basically reduce the amount of data that the detector has to go through. So let's say you want to detect solar panels on buildings on the whole country. The detector will not look at farm fields and mountains and stuff like this.
Again, assuming we're using a web map service here, does the detector itself, does that take care of the polling of that web map service? Because you're going to have to go back and forth quite a bit, I'm assuming, with different bounding boxes, making different queries, receiving that, like getting the image back, understanding whether the object is present or not, and sort of, moving forward in that way, possibly across an entire country or an entire city. Is that all built into the detection, or is that something that I need to think about?
No, it's actually all built in, and we spent quite some engineering effort on getting the the WMS and processing right, let's say. So as you say, basically with WMS, what we'll do, if you have detection area, is the detector will query for each detection area, the bounding box of the detection area, and then it will process this image. To make this faster, we have this is happening first in parallel. So we have multiple machines actually pulling the data from the WMS to make it faster for you. And we also have some caching. Like if you retrain the detector on the WMS, we are not going to refetch the whole thing again, but we'll fetch it from our local cache, and it's going to be much faster. Complexity of detecting on the WMS is completely hidden. So like you just click a run button on the UI, and then it's running in the background, and it will tell you when it's done.
I'm really excited about this. I think this is absolutely brilliant. I love the idea that, I could be involved in this, you know what I mean? And it changes the way I think about web map services. Up until now, anyway, I've thought about them as being, a base layer, a sort of a visual layer in my web map, for example, something in the background that gives context, but not necessarily something I can use to create data from, just because it's so labor intensive going in and digitizing things. But this changes the way I think about aerial imagery, and especially aerial imagery presented as a web map service.
Yeah, and I think it's pretty new for a lot of people in the field, actually. I mean, if you talk to people, they usually don't have it's not in their mental model that you can actually process WMS data. It's true that it's usually just used for visualization, but at the end of the day, from a technical point of view, it's just an image. So it's an image, and you can process it as any other kind of image. But I think it's really interesting with WMS, because also if you talk to some satellite image provider, they actually have different licensing model if you access it through WMS or if you access it as a geotiff, like as an image. And then when you go to them and you tell them, look, we can process WMS, it kind of explodes their whole mental model on what you can do with WMS. So that's also an interesting conversation to have with some big WMS providers.
I know from a previous conversation that you've got this really interesting use case in Denmark, which is where I'm living at the moment. So this is particularly interesting for me. Would you mind just walking the listeners through how you used this service to detect slurry tanks in Denmark based on a web map service?
Sure. So actually, at the end of 2019, a Danish company called Seges. So it's a company actually doing consulting work for farmers and working for the government of Denmark. So they came to us and they had this problem and actually a very short deadline. So it's something they came to us with at the end of November, and they wanted to get it done for the end of the year. So the deadline was pretty tight. And they said, okay, we have to actually estimate the ammonia emission from slurry tanks over the whole country of Denmark. And so there are about 35,000 farms in Denmark, most of them having slurry tanks around them. And slurry tanks is not something that's mapped. Like it doesn't appear on the cadastre. They didn't have any map of slurry tanks. But what they had was they had imagery, basically. They had the WMS with aerial imagery for the whole country of Denmark. And so they thought that we could actually detect these slurry tanks. And then from basically the area of the slurry tanks, you can estimate how much slurry is contained, and then you can kind of project ammonia emission from this. And so we gave it a try, actually. It was really interesting. So what they did is they connected the WMS to the platform, and then they started training a detector. So in their case, they detected also, they trained multiple detectors because they wanted to detect slurry tanks and then slurry tanks with roof, let's say, the covered one. But so they ended up training 2 detectors. And the way they did this is we started very iteratively. So we told them, okay, look, start with 20 annotations and let's see what happened. And so they did this and it worked quite well, actually, but not quite well enough for them. And so they iterated a few times. And after a few iterations, it took like just a few days of iteration and a bit of trial and error. They got a working detector with 57 annotations. And we were pretty amazed with the results, actually. And the reason they were able to actually get like really good accuracy with this 57 annotation is because they were using detection areas. So as we just talked before, detection areas are a way to constrain the detector on certain areas of your image. And so in their case, what they had is they had the location of the farms in Denmark. So they were able to do basically a buffer, like a circle around each farm, and they used this as detection area. And so it means when training the detector, they only had to focus on slurry tanks and really the appearance of slurry tanks. But for example, they didn't have to bother having it detect well in cities or whatever other areas that are not containing farms usually. Yeah, and at the end, they ran the whole detection over the whole country. We processed, the detector went through about 1 terabyte of data, like of imagery data, to process this. And I mean, it ran for like a day or something like this. So it was, given the amount of data, it was pretty quick to run, let's say.
This is mind-blowing for me. So I think you said 57 objects were detected. So a human went in and labeled or drew a polygon around 57 objects, and then we could run this accurate detection based on a WMS service on aerial imagery across the entire country. This is incredible.
Yeah, we were pretty surprised and happy about it, to be honest. But I think so one of the reasons why it worked so well with so little annotation was that the object is not super complex to begin with. I mean, a slurry tank is basically a round-shaped object with some brown stuff inside, basically. And near a farm, there aren't many round-shaped objects. I mean, usually there are silos, but this one, they have a roof and they look very much metallic. And so it's a pretty, let's say, unique object in the detection areas that they had. So that's one of the reasons why it worked so well with so little annotations.
And living in Denmark, I know that VMS service, WMS service, excuse me, it's amazing. Like the data is really high quality, really high resolution. It's all taken from the same sensor at the same time of year, and it's amazing data. So I think you had a pretty incredible data set to work from. I'm wondering though, so it worked really well in Denmark with the slurry tanks based on this incredible data. Does that then mean I could take the same training data set that I've created and move it to Canada, for example, and run the same and expect the same kind of success rate?
Yeah, that's a very good question, and I think as you said, it depends a lot on the quality of the imagery as well. And obviously, Denmark has a super uniform, nicely cleaned imagery. I think moving it to Canada. So first, I guess you should try a bit. So what you can easily do on Pictera is you can connect the Canadian WMS, let's say, and then you can train to detect on a few areas, and you kind of get a feeling for like, is it working well or is it a complete failure? And then from this, I think that the way we usually recommend that you go about generalizing a detector or applying a detector to a different kind of image is that you basically add a bit more training data. So you can keep all the training data you put for Denmark. This is all good and this is useful. And then you basically duplicate the detector and you add a bit more training data that is specific to the new region that you want to detect over. So you would add a few examples of slurry tanks over Canada, and then the detector should kind of learn about the kind of the diversity and cope with the difference in image quality, let's say.
Of course, that makes perfect sense. And that's kind of what I was digging after as well, is that I guess I understand this, that it really depends on the data. So I guess it would be foolish to expect it to work with the same level of accuracy if the data was completely different, if the resolution was 4 times that of the training data that you've used in Denmark. But I really like the idea that I can update the detector, that I can, use that as a base model and then go to, in this instance, Canada, find a service that kind of matches what I've been using here in Denmark, for example, and then update the model. So the work that I've done previously isn't completely lost.
Yeah, and it's something we are very excited about as well. So the way you can currently do this on the Pictera platform is that you can basically make copies of your detector and then kind of modify the copy. But what we really want to go for the future is that we want users to kind of think of Pictera as also an experiment workbench. So it's like it's a platform where you have your detectors, and you can run experiments on them, and you can copy them, you can add training data from different sources, and then you can basically train all these detectors with slightly different data and data sources, and then you can kind of evaluate them and select the best one for what you want to do. So it's also something, and this is something that you do if you're a machine learning engineer. You will spend your day basically running experiments and trying different settings. And so what we really want to do is to allow non-machine learning engineer and people with no coding experience to basically also do this experiment and make the best model that they can for the task at hand.
I feel like you've done an amazing job of sort of walking us through the data that we can use. We've talked about the different data types and what that data can look like in terms of the actual makeup of it, and the detection process, what that looks like. It was an amazing use case there with Denmark. But I guess we haven't really talked about what we get out of it. Could you talk a little bit about that? Is it bounding boxes of these objects that we've detected? Is it detailed polygons of it? Is there any attributes associated with that?
Yeah, so once you have run the detector, what you get is detailed polygons. So like the output of a detector is always detailed polygons. Actually, we have a detector setting that allows you to extract bounding boxes instead of polygons if you want. But if you like, you can have detailed polygons. And then what you can do from the platform is you can either export this detection as shapefile, as GeoJSON, as KML, as CSV as well. And then the polygons will have a few attributes. So currently what we automatically extract for each polygon is the area and the perimeter of the polygon. And then you can obviously open the exported files in QGIS, in ArcGIS, and do any kind of GIS processing operation you like. The other option with the results is that you can use a beta feature that we have to generate reports, basically. And what we call a report is basically a shared web map. Basically, you get a link to a map visualization of the data, of the output, and then you can share this link with clients, with colleagues, or with whoever you like, and they are able to basically visualize the detection and get some statistics about them.
I really love this process. I think I said it right at the start. Like, I love the idea that people like me that aren't machine learning experts, that we can be involved in this. And again, this really changes my understanding of web mapping services. With right now, in my mind, they've moved from just being that purely visualization layer to a layer that I can actually extract data from. Like me, I can extract data from it. So of course, we talked about Pictera as a platform, so you can do this on the website. One of the things I found really exciting is that you've taken the time to build plugins. So a lot of the people listening to this podcast will be very familiar with QGIS and ArcGIS. Could you take the time just to walk us through what that plugin looks like and what it feels like as a user?
Yes, sure. So currently the plugins are kind of in an early stage, I would say. So we are very open to feedback. So if anybody has any feedback testing them, we'd be happy to hear it. So the way the plugin works currently is they allow you to basically upload images directly from QGIS or ArcGIS to Pictera. So you don't have to use the upload UI of the platform or even open your web browser, but you can directly upload the image from your plugin. You can also access detectors and run detectors on images, and then you get the results automatically as a layer in your GIS software. So basically, it's really a way. I mean, if you're really used to working with QGIS and ArcGIS, it's really a way to speed up your workflow. So you don't have to open a browser and go through our UI, but you can, in a few clicks, you can basically upload data, detect, and then get the results as a new layer in your GIS software.
One of the things I find really interesting about this is, again, that web map service and like detection based on that. Well, so let's say I pull a web map service into my ArcGIS or QGIS platform. How does that work in terms of do I need to have the program open for days on end while the detection process runs over all of Denmark, for example?
No, that's a good question. So currently Like you cannot directly add a WMS from the JS plugins. You will have to do the setup on our web UI. That's something that we have on our roadmap for the plugins. But once it's set up on Pictera, all the processing happens in the cloud. So even if you start the detector from the plugins, detection and all the processing and data fetching and all of this happens on our servers in the cloud. So you can then close your GIS software and shut down your computer for the night and come back in the morning and have your results.
Would you mind just giving us an idea of what objects we shouldn't be using this on? Because I personally don't believe that machine learning AI is the right solution for everything. Earlier in the conversation, we talked about that use case in Denmark where we had slurry tanks, and they seem like quite a simple sort of an object. Is there object types or something we should be avoiding trying to use this kind of technology on?
Yeah, that's a really good, and I think it's also a bit of a tough question because it's really hard to say without trying. But I guess usually if the object can have very different appearances, then it will be tricky to train a good model for it. So, I mean, for example, buildings are both easy and hard, depending on what you want to do. So if you're trying to do buildings in a city, for example, with machine learning, you can do it very well. But let's say you train a building detector on cities in Switzerland, and then you try to apply it in Africa or in Southeast Asia or whatever, the buildings are going to look completely different. And so the detector is going to completely fail to detect buildings. So I think the difficulty comes when looking at the object, multiple instances of the same object, you see that they have very different appearances, then it's probably going to be tricky for the detector to detect them. And also, I think another way to think about this is that the detector doesn't really have our understanding of the world, and like it doesn't really embed the constraint that we have about the world, that the building is usually located close to a road and stuff like this. So this kind of reasoning that we are able to do as humans is not something that the detector will easily learn with the current state of machine learning, I would say.
I was talking to someone from a company called Skywatch recently, and he was talking about cloud detection. And that sounded like a really difficult problem. So not only can you only see the object from a top-down view the entire time, but clouds can be discrete, they can be continuous, they're constantly changing shapes, they're at different heights. And when I think about problems that would be difficult to solve in terms of using a detector like yours, I think about sort of naturally occurring features. I think about trying to detect a stream, because all streams look different. They have a different shape. They have a different width. I think about things like vegetation, perhaps trees, for example. I imagine that would be a really difficult problem to solve.
That's a good point. And I think also on Pictera, you can do two broad types of detector. So what we talked about the most is detectors that we call count detectors. So it means you're more interested in counting individual objects, and so detecting well each instance of an object. The other type of detector you can do on the platform is what we call segmentation. And this is detectors that are more interested in mapping areas, basically. So you don't want to count individual objects, but you just want to map an area, let's say, of grass or something like this. And so I guess if you're talking about vegetation, usually it's more in the segmentation bucket, let's say. Obviously, you can count individual trees if you have, but I think you need really high resolution image. You might need some also point cloud data to be able to do that well. But what you can definitely do is like map the area covered by a forest and stuff like this.
Julian, I really want to thank you for taking the time for teaching us all a little bit something about the work that you're doing at Pictera, about the potential that's here in the system and the software and the platform that you've built. I think it's really exciting, and I'm sure that's come across in my voice and my line of questioning during the interview. I'm all in on this. I think it's cool. You've got a couple of different plugins there. We've talked about them briefly. Would you mind just to round off the conversation and perhaps let us know what we can do to help you there? I know that you're looking for help, that these plugins are in a beta version. If people are interested in trying them out, if they're interested in getting involved, what can they do?
Yeah, so first, thanks for having me. It was a really interesting conversation. As you said, we are working also on the plugins all the time, and so we are especially interested in feedback on them. And so we'll set up a landing page on our website where basically listener can get 500 megapixels for free on Pictera if they give us some feedback on the plugins. So I think we'll just link the landing page in the podcast description. Yeah, and that's then get in touch with us and let us know what you what's missing, what you would like to do, what you tried, and so on.
Thanks again, Julian. I've really enjoyed the conversation, and I will be sure to put those links in the show notes and have them available on the website. So really appreciate your time. I've really enjoyed the conversation. Thank you.
Thank you.
So I really hope you enjoyed that conversation with Julian. I am genuinely excited about this. I love the idea that this object detection can run on a web map service. And I mentioned this several times during the interview that for me, a web map service has always been like a way of protecting data. Here's a picture of my data, but you can't actually get access to this data. It's more of a base map than anything else. And I think that this really changes all that, because if I can extract data from a web map service, I think it's really interesting, and I'm sure there's going to be a ton of really interesting use cases built around this, and I think probably there's going to be some businesses built around this. Anyway, if you've got a business idea for this, if you've got a use case idea for this, I would be really interested in hearing your thoughts. I'd be really interested in knowing if you can see the same potential as I can, or if I'm just off on some weird tangent. On another note, when I was talking to Julian after our conversation, we were discussing some of the sort of ins and outs of polling these web map services. And in the past, I've used a product called MapProxy. So if you don't know about MapProxy, it's well worth checking out. So as the name suggests, it's a proxy service for these different sort of web map services and tile services, and it has a ton of functionality. And it's a really interesting thing. It's a Python-based piece of software. Free, open source, really good documentation. I'll put a few links to it in the show notes. And the reason why I mentioned MapProxy here is because Julian said that part of the functionality that they are using to poll these web map services is based on the code from MapProxy, or some of the functionality in MapProxy. So I think it's probably worth checking out if that's something you're interested in. So again, if you're interested in helping out Pictera, if you're interested in trying out this product for yourself, go along to pictera.ch/mapscaping. It's a bit of a mouthful to say, so I'll put a link in the show notes, and you can check it out there if you want. They offer a few free credits so you can get up and running with the system. And again, I know that they would really appreciate any feedback you had if you're interested in trying out their plugins to ArcGIS and to QGIS. And that's it for another episode of the Mapscaping podcast. My name is Daniel. It's been a pleasure being your host again this week. As always, you're more than welcome to reach out to me on social media. I'm most active on Twitter and LinkedIn at the moment, and you can find me under Mapscaping there, or just search for host of the Mapscaping podcast. You can also find us on the website. There's an email address, all those things there. So yeah, if you're interested, reach out to me. I would really love to hear from you. Hearing your suggestions, comments, and feedback really helps me shape the direction of this podcast and lets me know what you're interested in. It gives me an idea of how I can make this better for you. So any and all feedback is greatly appreciated. Okay, that's it from me. We'll talk again next week. Bye.